In this video, I'd like to talk about binary trees. So binary trees are a type of tree data structure where each node inside of it has two children underneath it, right? So this is a very simple binary tree with just three elements within it. And one of the important things to note about binary trees is that for each node, it has a left node and a right node, or a left child and a right child, right? One of the most common applications for binary trees is actually used for sorting data and keeping data in a very sorted fashion. For this example, I'll throw some numbers in here. With this binary tree, which is containing the numbers between 2 through 8, and it does so with this root of 5, it's keeping it in a very sorted fashion. And it may not look like it at first, right? We sort of just have this random scattershot of numbers. But the rule of thumb here is essentially that for every element inside this tree, all the elements in its left child will be less than that element, and all the elements in the right child will be greater than that element. So, for example, let's imagine we are constructing this tree for the very first time, and I want to insert some data into it. We start with an empty tree, and I want to insert the number 5. Well, we have nothing in this tree yet, so 5 is going to become our root node. Then I want to insert the element 3. 3 is less than 5, so I'll put it on the left side of 5. Now let's insert the element 4. Well, 4 is less than 5 and greater than 3. So I'm going to put it on the left side of 5 and on the right side of 3. Now if I go to insert the element 2, it's less than 5, so I traverse down to 3. And then less than 3, so I'd put it at this position here, 2. You can kind of see how this is starting to be assembled. If I insert the element 7, that's going to be greater than 5. So I end up with something that looks like this. If I want to insert the element 6, that is greater than 5, and then less than 7. So I'm going to insert it on the left side of 7. And if I want to insert the element 8, it's greater than 5 and greater than 7. So I'm going to put it on the right side of my 7. Something like this, right? These two trees, this one I just sorted initially right off the bat for you, but with this one, it's a good example of how each one of these elements, as they're getting inserted into it, would maintain this sorted functionality, right? Now, one of the really great things about binary trees like this is they sort of lend themselves to this log n runtime, so these log n algorithms. For example, one of the things that we've talked about previously is binary search, which is a search over a collection of data where you are essentially picking a center element and then deciding whether or not the element you're searching for is on the left or the right side, if it is greater than or less than that center element. This binary tree data structure essentially does something very similar already for us, just in the nature of how it's storing the data. So if I wanted to search for the value 4 inside this tree here, I could do that incredibly quickly. I look at the number 5, my root node, and I say, is 4 less than or greater than 5? It's less, so I traverse down to the 3. And then I say, is 4 greater than or less than a 3? It's greater, so I traverse to the 4, and here I am. After only 2 comparisons, I've found my element 4. If I want to search for the number 12, to see if 12 exists in this tree, I can take my number 5, start my root node. I'd say 12 is greater than 5, so I'm going to traverse to the right. Here at 7, I say 12 is greater than 7, so I traverse to the right. Here I say 12 is greater than 8, but because there's nothing to the right, I know that 12 doesn't exist in this data structure. This sort of search algorithm it's essentially a binary search, right? It's doing this tree traversal through this data structure here. This is one of the reasons why binary trees are used so commonly for storing data. And actually, some of the data structures that you may frequently use, such as maps or dictionaries, may use these binary trees as a way to index into them very quickly. Dictionaries and maps use binary trees or some type of tree data structure very similar to this to store their data, where the keys in their maps or dictionaries are these elements here, the elements that are being compared to one another, how they're organized within the tree. And then that way it makes it very quick whenever you're trying to access elements inside those data structures. Now, as a random side comment, this is also why with maps and dictionaries, the keys to these data structures need to support a comparison operator, because to insert anything into this structure, you have to be able to compare it to one another. I'm comparing 5 and 3, and if we use something else that are keys, we have to be able to compare these elements to each other so we know whether things should be on the left or the right side. Right? This is one of the big benefits of binary trees.